on to the next talk by Zhou. I guess title is going to show up soon.
Okay. It's there. Okay, but it's on myself.
Thanks for the opportunity to speak here. Today I'm going to talk about something extremely simple. This is related to previous short talks this is about generalization of Latin entropy and holographic field. It's based on a recent paper with two great students who are going to apply PhD course this year. So the motivations, we all agree that with this quantum entanglement played an extremely important role in understanding NCTS. Indeed, the celebrated success, including the kind of black hole commutative double resonance, and the Ryu-Takelage formula, and the HRT formula, and dynamics. But still, there are some unsolved problems or issues. Let me raise a few of them. First of all, the mixed state entanglement measure is best known, including its holographic field. And the second is multipartite entanglement measure, and the holographic field is less known. And of course, the general quantum information dictionary of ASFT is unknown yet. So this is the standard page. I guess you saw before. To solve some of these remaining issues, there are proposals, say in ADS holographic side. Say this is the ASFT. Just pick a constant time slice. For some case, we consider a static system. For time slice, this is my time slice. There are proposals in the ADS side, something so-called entanglement wedge cross-section. This object, which denoted by this dashed red line, a proposal to characterize the entanglement or correlation between the part A and B. This was interpreted in CFT language as the so-called entanglement of purification by the two groups. And also, there are some other identifications to the CFT quantity, like raising productivity, order entropy, including the recent one, which is reflected entropy. Sounds quite interesting, which is I'm going to focus on today. Well, a little bit thought will tell you that why this red dashed line is better than the entanglement entropy to characterize the correlation between A and B for the mixed state of B, which geometrically you can check is a reasonable quantity. So this kind of idea was generalized to multipartite or n-partite case. Geometrically, this is also a very simple configuration, like a triangle. But you might wondering why you pick up this triangle type, why not other type? For instance, there's some sort of line type or star-like things. But you can easily check that candidate is not as good as this one, or to satisfy some simple consistency condition. For instance, when maybe say are pure, you have to go back to some of the entanglement entropy, but some other configurations does not. So in this paper, this triangle type was trying to identify it as the so-called multi-peptide generalization of entanglement purification. And a lot of evidence has been checked to support this one, but there's no direct implication. So the problem here, or including the previous proposals, the key issue here is this kind of information quantity was defined using the optimal procedure. It's kind of minimum, you have to do optimal searching, which makes the computation, real computation, extremely hard. So far, there's no direct check for this kind of proposal. So today we're going to with another proposal which can be computed explicitly. So this relies on some idea called canonical purification, as mentioned in yesterday's talk. So consider mixed state, Rho AB. Well, very intuitively, how to understand this kind of purification and why this is canonical, you can understand it this way. So if you do the decomposition or Schmidt decomposition for any given mixed state, you have some kind of base, right, like this. Ij, one is bra and the cat. One is cat, another is bra. But you can flip this bra, it's right, J is bra J to cat J, right? But keep maintaining this coefficient in front, right? Then you somehow, by force, you get some pure state with a similar coefficient with the previous mixed state. That's the idea of the canonical purification. The point is mathematically, this is really a canonical procedure. It's not an artificial one. If you have mechanical, this is canonical. So structural language is just stated as this one. So we denoted this purified state coming from this canonical procedure as a sort of severity rho, with that. So this belongs to a double Hilbert space. This is reasonable because the purest one you only have a Hilbert space which is running over all the i's, but here now you have both I and j, right? J and I are very another copy of the Hilbert space. This new state belongs to a double Hilbert space. Again, this is not something artificial. You can do explicitly look at this example of, let's say, Rho AB, given by this kind of up and down mixed state. You can easily check it. You can do the canonical purification, you get the Rho. Okay? Just double a Hilbert space, you get a pure state. And you trace over this A prime, B prime, you go back to the B. Right? So, I mean, why, then you might wonder why you put the severity, there's a funny severity here. Simply, again, because there's a half, there's a 1 over square root of half. This severity just means the severity of the matrix coefficient. So all this can be done for any given mixed state canonically. So we defined entropy, which is called a reflected entropy, for the reason why reflected, for the reason we'll see later. In holographic, it's more intuitive why it's reflected, because it really, the whole holographic coefficient is really like a reflected in the book. So, by doing what? By doing, now I choose to trace out the AA star right here, AA prime. And I'm left with BB prime. So if I do that kind of bipartite, then I get a Neumann entropy. This was defined as my entropy, reflected entropy in the double Hilbert space. So there are good properties. This has been checked in the paper. I'm sorry I didn't put the reference. I'm trying to mention by words reference. This is very last night. I didn't put the reference here, but this was checked in the paper by Fudan. There are good properties to justify this kind of entropy. Is a good measure, correlation measure for mixed state Rho AB, a good measure for correlation between A and B. But in order to do the further development, I would like to give a graph representation. We learned in text, we're going to use kind of many graph, Feynman graph. here I will also just put a graph. But whether this graph has clearly physical meaning is another question. First, let me just accept it as a representation of the procedure, previous canonical procedure. So you consider a one-dimensional, again, consider time slice, then you consider a one-dimensional quantum system. It can be discrete or continuous. Let's say from a circle, A, B, and the B to C. Now, since I need another copy of Hilbert space, I will pick up another circle, okay? A star, B star, and the B to C. So I graph the canonical purification procedure by you to pick up these two same cycle, but gluing along B to C. So what I left with is the A star, B star. So this is the graph according to the previous canonical purification procedure. So now, after you get a pure state, so you should understand these two as kind of this patch and another patch. Of course, we are going to focus on the boundary in order to view this geometry clearly. You have to think about this as kind of two disks, okay? You glue along B to C. So if I get a big pure state, I can try to draw some curves. This is some curve to separate the whole pure state into two. In this case, I draw a curve in this way. If you view this patch, it is just the curve. Go to first disk, another disk, close. Then this curve separate the A star and B star. So I view for any such kind of curve which did the bipartition, I can canonically define the entropy, moment entropy for each radical. Of course, this looks very trivial, but this doesn't prepare for the later discussion in order to let you keep in mind the green. Now, we consider generalizations. So what's the idea? The idea is to consider a little bit more complicated, slightly more complicated. Let's say I have A, B, C, okay? Or the opposite part is leader B, leader C, leader A. Okay? So why I put the leader letter A, B, C in the capital A, B, C? Because eventually I want to glue along all the leader letters, but pick the capital A, B, C remain. Okay, let's do it. So we can first glue it along letter C. What I get is something like this. Right? Now, this graph represented in the practice in the quantum information, this procedure really means algebraically this equation. I get a new state. I start from initial pure state. This closed circle represents the pure state. And capital ABC is some mixed state. Right? So I initiated with a big pure state, okay, density matrix. Now I traced over letter C, which essentially means I just move along letter C. C disappears in some sense from the boundary, right? So I get a density matrix after traced over letter C. For that density matrix, I take the canonical purification procedure, which I just mentioned a moment ago. That's why I put a square root here. I view this eventual state as the pure state. I mean, view this as the graph is not that surprising because in some sense you can view this as sort of a passing integral if you try to feel the inside of the circuit as a disk. For instance, in conformal field theory, there's a very similar language. You can write using a passing integral. You can write a state as a passing integral with a boundary. So this eventually means you just gluing different patches with passing integral. But by this moment, we just view this as a graph representation of the practical procedure I'm doing here. So this is the first step. You can do further. So after this one, we just arrived here. After that, I can do again. What I'm doing here is I can further trace over B prime and do the canonical purification. So this actually means what? But for each canonical purification, you need another double copy. That's my definition. So I need another copy of this one from here. Here is of course a pure state. Now I'm trying to trace out B prime and do the canonical purification. Means that I take two copies and I glue it along B and B prime. then I will get this one. So the logic here is that for any pure state, you can try to trace out some part of it, then you always get a mixed state. For any given mixed state, you can do the canonical bifurcation in the standard way. So you can do further. So you can trace over further. You can further one more stop. You can trace over what's that? Liter AA. You're only up to here. You all are the capital letters. You are only left with liter A, right? A1 or the copies. A1, A1 prime, A prime, A. Now I further choose to pick another copy, then I can trace over all liter A. So up to here, all the liter A, B, C are gone. I only left with capital A, B, C copies of them. And this is a bigger pure state. The data of this bigger pure state only relies on the initial three-body A, capital A, B, C density matrix, right? So you might say it's not obvious. Actually, it's obvious. How to think about that? You think about it, you choose another, you different liter A, B, C to purify this one. So after eventually those processes, finally, the big pure state will not depend on a slightly different liter A, B, C, right? Because all of them are traced over. So you get a kind of big pure state that looks complicated, but it's not that complicated. It's actually controllable. In your computation, you will see. So as said previously, we want to draw some red curves to bipartite the eventual big pure state to define the von Neumann entropy. Whenever I do that, I can define the von Neumann entropy, which is a very defined quantity. So in this case, I'm particularly interested in some von Neumann entropy or some bipartition which satisfy the permutation invariance. Really meaning that you cyclically take A to B, B to C, C to A. This quantity will be invariant. If this particular quantity is unmutual. So this is such kind of quantity. This kind of quantity. So all these different letters is associated with this big graph. I just choose this particular bipartition. So in order to compute this von Neumann entropy, you can always use this well-known trick, like rapid trick. So let's turn to holography. So far, nothing to do with holography. Let's turn to holography. So in holography, again, for a constant time slice, you don't worry about time, right? It's a static case. So in holography case, the question will be, for those kinds of different gluing construction of your boundary quantum system, what happened for the bulk? So you realize that together with the bulk, of course, the very intuitive idea is for the bulk, you have to also glue it in order to make a consistent configuration together with the bulk for the eventual pure state. Now, that's indeed true. So together with the bulk, it's not hard to realize that this is the unique choice. You can get the configuration together with the bulk to respect your previous boundary gluing process. So what does that mean? This means that the balloon line denotes this real Takanagi surface. Okay. For this AB, the balloon line is real Takanagi surface, then this patch was filled. This is real bulk. This is the ABS bulk. Okay. Then you should gluing along your real Takanagi surface, then you have a big bulk. Now, realize that in this way, then this has a very clear meaning. Then this will be related to previous entanglement wedge cross-section, which is graphed here. So it's clearly because there's D2 symmetry. This outer and the inside is just a two copy. So if you choose a minimal curves, which closed in this way, is certainly twice of this red curve. Just twice the symmetry. So you don't have the choice to close the minimal curves. Always twice. As we were saying, if you generalize it to 3-body or n-body, it's not true. You have many different options. So let's do that for the more complicated case. So if you have 3, okay, of course the gluing, I mean, in order to prepare a big pure state is never unique. You can choose many different ways. Okay, each eventual different big pure state is different, can be different, very different. Let's say, let's take this one as an example. I hope you understand what this graph means. So this just means you take a 2 circle, okay, together with the block, which means you have 3 segments with topological surface together with this block. You just took a 2 copy. You just once gluing along the 3 balloon segments. You just only 2 copies enough, right? All the liter ABC are gone. So you have such kind of big block together with the boundary. Now you choose a minimal curves wrapping this way. Okay, it's not hard to realize that this is related to for a single copy. Okay, you consider a bipartite for this ABC, which is divide A and BC. This is nothing but the entanglement cross section, bipartite A and BC. And this is double for this one, twice for this one. Because both have to be respected minimum. So you can if in the 4 copy case, you can also take a 4 copy, gluing somewhere. Let's say I arrive at this kind of thing together with the block. I can draw a curve in this way. This curve you can really choose by yourself. I choose the bipartition, I can draw a curve. I minimize this curve. I get a unique lengths or areas, okay, for this curve. So it's not hard to realize that you just trace what you do here, just mirror all this orbit. You see here, I go from here and then back to close this curve. So corresponding to the single copy configuration, what you do is actually, in this case, you just go from here, then you back, you check it, and this one. Then this curve closed. Because this is one of the reasons why this kind of configuration called the reflective. You see this like a reflective. It's like really reflective. So there is some inequalities because everybody respects the minimization. So there is a very natural inequalities we can establish among different objects. So in the 8 copy case, for instance, you can take this kind of curve. If you take this kind of curve, it's not hard to realize what you get something like this. Yes, please. And you back. And there's an alternative choice for the same 8 copy case, which we were interested in, particularly interested in this kind of thing. You don't go in the back, hopefully you can understand what this means. This is kind of a little bit complicated. 8 copy case. There's a boundary. You can view there's a big patch on this side, and the inside there's another big patch. These are boundaries. These are holes. There's 1, 2, 3, 4, 5, including inside. 6. There are 6 holes. Okay. You can choose alternative orbit this way. This is different from previous orbit in the back side. In the back side, previously you were going this way, but now in the back side you're going this way. So now there's some specialty of this configuration. What is that? So this whole environment has a center symmetry. If you rotate it in 180 degrees, it go back to the original one. Then you expect that the minimal curve also has to be respected at one. So then reasonably you can check that this point to be the same point of this point. Okay? What does this mean? This means that when you reflect, when you reflect go in this way and back, these two points have to be coincide. So this makes this triangle has to be closed. So this is distinguished with this one. As you see, it's not necessarily be closed. But after that, this minimal surface or minimal curve is very defined. You can minimize it. Well, so far, what are the graphs, simple graphs? You might say this is so artificial. So actually, every process here can be computable. As I just take the remaining 5 minutes to explain how to compute it. So you write the we just did 3 steps in order to get the 8 copy, because 3 steps canonical purification you can write it explicitly. So now there's a funny gluing process associated with this square root for canonical purification. As we learned from entanglement entropy computation, that whenever you have some sort of path integral gluing, you can always take use of the replic trick. So here we did the same thing. So we just extended the square root, which is a half, to a m over half, where m is integer. If we can compute for integer m, we just continue m to 1. So we're done. That's the idea. So it's not difficult to realize that this is the replic formula which can give this final entanglement entropy, Neumann entropy. Let's take one example. So first we do a soccer. Now we take an example to do the real computation. Let's do an infinite line. It's a ground state of safety 2, which is the ADS block. So now here the triangle configuration looks like this. So let's minimize it. Geometrically, this is a very simple exercise. If you minimize it, I minimize this theta angle. If you convert it to symmetry, so you can compute the geometric length. Now in CFT, you can do this similar things. Use the replic tree that I just introduced. So there's two replics. One is replic associated with the purification. Another is replic associated with the Rini index. Because finally we want to compute the entanglement entropy. So there are two replic directions. One is m. Okay, another is n. For m equals 2, n equals 3, we have 24 replic gluing patches. But it looks complicated, but it's not that. You can able to control it using this so-called twist operator language. So just counting all the conformal dimensions of the twist operators. The partition function in the replic space is associated with the correlation functions of the twist operators. Now, in particular, in the large C limit, everything simplifies. So how is that going on? So in this case, the previous configuration, I consider 3 intervals. So there are 6 endpoints, which means there are 6 twist operators. I need to compute a large C result of the correlation function of 6-point correlation functions. So in the large C limit, the 6th block, the result block, actually explodes in this way. So you only need to compute this liter f function as the xi. Because these are parameters, you have to compute the liter f as a function of xi. Xi is essentially my position of the 6 operators. So now this is was developed, the paper by Tom Hartmann. So this problem can be translated to a monodromy problem, essentially those equations. You can with these equations, I can given xi, I solve ci, which means ci as a function of xi, I can compute everything. So this is the result. So you compute this geometrical quantity and the CFT quantity, you see, you can get very good agreement. The one thing you have to look carefully is about this kind of computation never valid for whole parameter regimes, as you can imagine why. Because we essentially compute some blocks or 6 external points. So for some parameter regimes, it's a control parameter, different channel is dominant. So you expect only for some parameter regime, some block channel agree with your holographic result. Indeed, this happens. There's a liter disagreement when you tune your parameter to a large regime. You see, liter r goes to 10, some mismatch appears. So liter r is this length. So d1 is this length. So this is the d1 dependence. So for both these two shape, we get a fairly good agreement. Let's conclude here. So we found infinite many concrete CFT entropies, and its holographic review, as I showed you, there are different minimized curves and turn into a very different way. But the claim is all the CFT entropies can be explicitly defined, and there's a concrete duality found. And some of this duality has been tested or proved, and it's worth to push this idea to more interesting complicated background like black hole background or time binding case.
Any questions or comments? Okay, for a simple question, are your results for two-dimensional feasibility of for the general higher dimension case?
Yes, but the finite twist operator approach is very difficult.
Yeah, high dimension.
The computation, T computation. But all these proposals works for higher dimensions.
But in higher dimensions, when you consider the Entropy trick, then you should consider the backward action in the holographic side, which means the geometry is no longer ADS.
Oh yeah. Good question. So that's why it's reasonable, right? Because eventually we take a last limit, right? Yeah. Last limit is there's a lab name for last limit, which is semi-classic limit. But if the proposal is genuinely true, you can check even including back actions. But so far, this is only now semi-classic limit, which means that you disregard it.
Okay, so maybe due to the time, so let me move on to the next. Let's thank the speaker again. So the